Hello and welcome to another Zosin session. So let's continue working on Wang tile project. I'm going to put this, the link to the source code of this project in the description. So source code. So it's basically a very simple project that basically generates different patterns using Wang tiles. You can read more about this kind of thing in the README. So I put a lot of information in here. And let's take a look at the current state of the project. I haven't touched this project for quite some time, so let's see. So we have a couple of stuff that is modified in here. I don't think these are very important modifications. I'm gonna just reset everything. I was just experimenting with things. Oh, I forgot that this thing doesn't use make files. It uses no build system, our own custom build system, for whatever reason. So let me finish the other stuff. Maybe there is something new I worked on off screen. Sometimes I do that, like, you know, small things here and there. So yeah. Looks pretty good. And essentially, let's actually clean everything and rebootstrap the build system. So we start fresh. And yeah, so this is the current state of the folder. If I run the entire thing, right, so it will generate two files, atlas png and grid.png. So if I take a look at the atlas png, thank you, Fech. So I need to put some sort of like black background so it doesn't ruin my encoding. So it generated the Wang tile set, and the point of the Wang tiles is that Wang tiles, the specifically tiles that we're looking in this specific project, are square tiles with two colors, right? So each side has one of two colors. Basically this is the full Wang tile set, right? So since you have four sides and two colors, 2 to the power of 2 is 16. As you can see, we have 16 tiles in here, right? So, and the idea of the Wang tile set is to, using this tile, style the infinite surface. And the constraints that are applied is that the adjacent sides have to be the same color, right? So, and the second file here basically does that, right? So as you can see, it's using Wang tile set. It generates like a Wang tile grid, and it makes sure that the adjacent sides have the same color, right? So that's basically what we have in here. And we have different, like right now, two kind of patterns. It's this like digit-like pattern, and the second one is just like a sort of circular gradients pattern. I can try to enable it super quick. So let me see. So I think if I try to look for digits, so I think it's called blobs, and specifically for the blobs, it would be nice to set different colors, not black and white, right? Something like this. And let's just do no build run, right? So, and if we take a look at the atlas, black atlas png, so here's the atlas, right? So as you can see, it's the same principle. Each tile has four sides, and each side has two colors, right? In this case, it's red and cyan. So, and if you try to generate a grid out of that, this is how the grid will look like. So yeah, we have two patterns. So we have a little bit of a parallelization. So do we even report the amount of threads we currently working with? We don't really report that, but yeah, we have a little bit of a parallelization to speed things up. Not really to speed things up, it's more of a like a see how it will fit into the whole renderer idea. So we have a macro called threads, and that macro controls how many threads we create when we render the atlas. Right, so basically we allocate an array of p threads, so we're using POSIX threads for the entire thing, right? And then we just start this amount of threads, initializing, like giving all of the necessary information for the thread, and we just run it, and then we wait until all of the threads are finished. And in each individual thread, I think render atlas thread, right, so we're rendering the tiles. So right now, we're only using multi-threading for generating atlas, right? For generating atlas. So, and essentially how it works. So let's actually draw the atlas grid. So atlas grid, as far as I know, is 4x4, right? So this is a 4x4. 4x4. And let's say that we have 4 threads, right? So the amount of threads is equal to 4. So what we do, we spawn a first thread at the beginning of the atlas grid, and then we say that the step of that thread is going to be 4, right? So the step is usually equal to the amount of threads. So, and then we step 4 tiles further, 1, 2, 3, 4, spawn another thread, right? And we tell the thread that its step is also going to be 4. So, which is kind of strange. Is that how we actually do that? I actually doubt that, because, oh, I just realized that no, we actually spawn the second thread in here, right? And the third thread in here, and the fourth thread in here. And for each of the threads, the step is going to be 4. And the reason why it's going to be 4 is that once thread finished rendering the first tile, it will step, how to say that? It will step the amount of tiles equal to the amount of threads and switch to here, right? So then this thread is going to color this tile and step 4 times, and then it will color this one. And as you can see, basically what they're doing, they're coloring their individual rows, right? So never overlapping with each other. So, and yeah, so that's basically how it works. If you have less threads, it still works because they now step less times, but still doing all of that in parallel, and so on and so forth. This is how we're doing all that. So yeah, that's pretty cool. But we also have an interesting mode where we can try to render the entire thing in a more or less animated fashion, right? So this is basically how it looks like. We're trying to animate the grid, and we're doing that by constantly regenerating the atlas, right? We constantly regenerate the atlas. But the problem with constantly regenerating the atlas is that you constantly need to create a bunch of threads, right? So you create a bunch of threads and then you wait for them to finish, and you have to do that on each individual frame to make the whole thing animated. And I don't know why, but it feels like the creating a thread could have its cost, and it would be better to just create n threads and just constantly reuse them for rendering. I know nothing about multi-threading programming, so I just assuming things, but I think creating threads over and over again does have a cost. Otherwise, we wouldn't have such a concept as a thread pool, right? So if creating a thread didn't have any cost, like why would you need a thread pool, right? So that doesn't make any sense. So that means there is some sort of a cost, but I think it's kind of difficult to measure that cost. I don't know, we can do one thing. We can do one interesting things. We have a simple profiler, right? We can have a simple profiler that lets us actually measure the time between 2 points and then like report that time somehow. Okay, so let's actually try to use that. I'm gonna create like a second entry point, right? Oh my god, 666. Oh, anyway. So, and let's, I don't know, implement something like maybe we can find a sum of numbers starting from 0 to 10,000. I don't know, just to demonstrate how our profiler works. Right, something like that. Of course, you can use the formula, but using the formula will not properly demonstrate the profiler. Right, so, and I think you do something like begin clock. Yeah, there we go. So you have to call the function begin clock sum, and you have to provide the label because the label will appear in the summary, and then you end the clock, right? So you have a sort of like a clock brackets, right? You have some sort of clock brackets, and after you're done, you can do something like dump summary, right? And you can dump the summary to, I think, stdout. So that's a very simple profiler that we can use in our application. And as a matter of fact, this is this you know, performance summary generated by that profiler. So if I now try to run the entire thing, right? So it says that computing the sum took So this is a millisecond, 25 microseconds, I suppose, right? So we can try to run it multiple times, and it's around like, you know, 30 microseconds. So we can try to increase the sum. I think we're also disabling all of the optimizations, right? So we're not running any optimizations. Okay, so yeah, now it's 300 microseconds, right? So, and what about the million? Will it be a millisecond? Unoptimized, by the way. This is all unoptimized, right? 2 milliseconds. Okay, so we can clearly see that it's growing. 2 milliseconds, and what about 10 millions? What about actually billion? I think, can modern computers compute billion fast enough? 2 seconds. Okay, I don't really have a modern computer, right? It's just a pretty potato laptop, but it is what it is, and it isn't what it isn't. So this is how we can measure the performance of these things. So we're using, I think, I don't remember what we're using. Get time, yeah, clock get time, which has a very high resolution. The resolution of this thing is nanoseconds, as far as I know. Yeah. So, and you can, you know, measure time with this thing, which is very convenient. It doesn't work on Windows, but on Windows, I think you have other functions like query performance counter, right? Query performance counter, and I'm not sure if it has the same resolution, but people usually use that function to do profiling. I don't know. So. And maybe at some point we're gonna port our wank tile thingy to Windows, and we're definitely gonna be using this thing instead of clock get time. Anyway, so what I want you to do, I want you to measure how much time it takes to create a thread, like roughly. So let's go ahead and create a thread. Pthread create. So this is the function we need, not the function we deserve. So we have to provide the pointer to the ID of the thread, so it will return it through that. Then attributes, as far as I know, you can just put them, you know, null. You can just put them as null, and then the routine that will start, right? Then the routine that will start. Okay, so pthread t thread. Right, so I'm not going to check for the errors in here, but because I don't really care. So here's the thread. The attributes could be null, and so let's call it something like thread main, right? So thread main. As far as I know, this thing has to return void star and accept void star, and that's basically the argument that you pass in here, right? We don't really care about that argument, so we're not going to pass anything in here. Thread main, there we go, we're creating this entire thing, and that should be fine. We might as well print something. I'm not sure if it's a good idea to print anything in here, but okay. Print thread main, right? We're gonna join the thread anyway, right? Just to make sure that we're not, you know, doing anything weird with IO into separate threads, but maybe it doesn't really matter. Maybe it's totally okay, right? So, and I want to join the thread actually outside of the clock brackets, right? Because I don't want it to screw up the time, right? So I want to only measure the performance of just creating the thread, how much time it takes to create the thread. So I'm going to provide the thread, and I think this one is not important. This is going to be just purely null. And there we go. So how much time usually takes to create a single thread? So, and in here we probably want to return null. Right, so let's go ahead and do that. So we have to provide the pointer, I think oh yeah, okay. So it's not visible outside of this entire thing. Maybe I'm going to keep the brackets just in case, because they sort of emphasize the block. Unused parameter, expected expression void something. Oh yeah, okay. So, and since we're not using this parameter, I'm also going to quickly ignore the entire shit. There we go, finally, and 78 milliseconds, actually, microseconds, I mean. So I forgot to put a new line in here. Not that much, to be fair. But I have a feeling, by the way, I have a feeling that this is not the full picture of the story. It's around like summing up like, you know, 10,000 numbers or something like that. So it's pretty negligible. But I mean, if you do that multiple times in the frame, so as a matter of fact, how many times do you do that? So we do something like thread, right? So yeah, let's actually try to mimic this entire thing. So we're gonna do threads, right? We're just creating threads. Let's not do anything inside of these threads. Create thread, right? So this is going to be that thread, and we have to do we have to iterate them. Size t less than threads plus I, and there we go. So we create the thread. And then we need to join them, right? For size ti threads plus I. There we go. So let me see. Is that everything? I think that's everything. Let's see. Something went wrong. I'm not sure what exactly went wrong. Oh, I think I do know what exactly went wrong. Okay, so the compiler wasn't even complaining about that. Why am I not running the compiler from Emacs? I don't understand, because it allows me to quickly... okay, so yeah. All right. So it's like it doesn't go to 1 millisecond, but if you're running this kind of thing on each individual frame, right? On each individual frame, it can stack up with all of the other operations. Yeah. And what's important, if you want to run at 60 frames per second, right? If you want to run at 60 frames per second, you have to stay within this value, right? You have to stay within this value, because that's 60 frames per second. If your entire frame takes more than this, that's it, you're done. You cannot run at 60 frames per second, right? And if creating n threads, in our case I think 5, takes this amount of time, and this is one of the operations you're doing, that's a pretty expensive in terms of like running at 60 FPS. You don't really want to do that, I think. But on top of that, we're also, I think, waiting for them to join, right? We're waiting for them to join. So if we include waiting for them to join and collecting this stuff, how bigger it will become? Well, it's really, sometimes it even takes, it breaks into milliseconds. Look. So sometimes it even breaks into milliseconds. So it is actually quite expensive. We're not even doing anything within these things. We're not even doing anything. We're just creating the threads and we're just joining them, and we're already breaking into milliseconds. And you can have only 16 milliseconds in a single frame. So it wastes an entire milliseconds out of 16 that you're allowed to have, but you also have to do a lot of useful things. Right, here's the thing. Here we're not doing anything useful yet. So there's nothing useful here yet at all, but we need to do something useful, like computing the tiles and stuff like that. And that takes also time, right? And this kind of stuff stacks up. Another interesting thing, but again, I know nothing about multi-threading. Take everything I say with a grain of salt, right? So it's just like conclusions that I come to by doing these small experiments myself, right? Do your own experiments and see if you can come up with the same conclusions. Also read more information about this kind of stuff. Please don't listen to any of my advices about multi-threading, because I know nothing about multi-threading. I just conduct experiments, confirm my hypothesis, and that's it. I'm not doing anything fancy in here. And yeah, I definitely never worked in commercial projects that do like serious multi-threading. I'm just sitting in my, old Soviet apartment doing some stuff on the internet. That's it. I'm a simple person. Anyways, I wanted to measure another thing actually. How much time does it take between creating the thread and the thread actually starting executing? So, because, okay, maybe I created the thread and the execution continues, but maybe there is some time between like creating and actually starting doing some work, right? Because I presume that to create a thread, you'll have to go to the kernel, right? And maybe you just say to create a thread and you continue executing, and the kernel actually takes some time to create the thread and actually start it, right? So maybe there is some time between like that and that. To be fair, the join kind of includes that time if you measure the join, so the time will be included, but it will be interesting to see how much time it takes do that. So let's actually create a single thing in here, right? And I have an idea how to measure that, because basically we need to measure time between 2 points in different threads, right? So we're gonna start measuring the time. We're gonna start measuring the time in this thread, but we're gonna end measuring the time in this thread, right? So we're starting begin clock here, and then we're ending it in here, in a separate thread completely. So then I'm gonna also join this thread. I'm gonna join this thread, and I'm gonna provide a new one here. So let's actually see if that will work, because the profiler was not designed to be multi-threaded, right? So when we begin the clock, after this function, we're not doing anything with the clock, so it's totally fine. Then we're creating the thread, and we're joining it and not touching anything. So it is safe for this thread to touch the profiler. And once it's finished, we touch it in a separate thread. I don't see any synchronization problems in here, right? So nobody's trying to access the profiler at the same time. They're sort of doing that, you know, sequentially. At least this is how I see that. I might be wrong. Please tell me in the comments if I'm wrong or not. But I just want to conduct an experiment, right, and see how much time it takes between actually creating the thread. And honestly, do we include join? We do freaking include join. Well, we don't. If you think about it, we don't really include the join, right? Because it can stop measuring the time while being inside of join, so join is not really included that much. But yeah, so there's still a lot of time between actually starting the thread, and it even sometimes goes to the milliseconds, of course. Yeah, so there's a lot of time between actually creating the thread and then doing the useful work. So you don't want to, at least I think, we don't want to recreate the threads all the time. But the question is, how can we not do that, right? How can we not do that? Like, because we need to sort of, because we're using creating and destroying threads as the ways to synchronize all of the threads that construct the, you know, the atlas, right? So, and I think this is an opportunity to look into a very interesting synchronization primitives called barriers. So Pthread Barriers, yeah. So using barriers. So maybe I'm gonna look into, yeah, Pthread Barrier init. Oh boy, I think I need to make a small break because I've been talking a lot. Right, okay, so let's actually make a small break, and after the break we'll look into barriers, and we'll think how can we apply the barriers in our particular situation to not constantly recreate the threads to, you know, re-render the atlas and stuff like that, and maybe we'll be able to speed up things. I don't know, we'll see. So all right, before saying that we need barriers, let's actually try to understand what we need, right? So we're trying to render at 60 FPS. So how do we start a frame? So start, I want to actually use the green one. Let me put it somewhere here. Start frame. At the beginning of the frame, what we're doing, we are generating the atlas, right? Generating the atlas. And while generating the atlas, we actually spawn a bunch of threads, right? So create thread, a thread. Just a second. Excuse me. Excuse me. So we created a bunch of threads, right? Then we collect. Well, we don't collect anything, right? So it's already collected while the threads are generating the tiles. They're putting them into this like thing. Then we generate the grid, right? Generate the grid. And generating the grid is basically creating the array of the size of the grid, right? And filling it up with masks called BLTR, right? So essentially, as already said, wank tiles are the tiles with two colors on each side. And we encode that information with the bit mask, right? So basically a simple bit mask, a simple value from 0 to 15 fully encodes a single wank tile. And essentially what we're doing here, we're creating an array for the size of the grid that we want to generate, right? So let's say that, for instance, we're trying to generate where is the grid? I cannot see it, so here is the grid, like something like this. We're creating the array of the size of this grid, and we're filling that up with values like 0, 1, 14, and so on and so forth, right? And we also try to match the colors of the adjacent tiles. So these values may not necessarily actually match, so I just put them as some values in the range between 0 and 15, right? So it's just like, that's basically what we're doing. This is basically the step of generating the grid, just figuring out what tiles need to go where, not rendering the tiles themselves, but figuring out where they will go. So this is basically generate the grid. So here's the generate the atlas, then we're generating the grid, and then we render the grid, the grid. That's a completely different story. Well, not completely different story, but I mean, yeah. So we're creating yet again an array of the size of the grid that we want to generate, right? Something like this. I wish there was a faster way of drawing grids in my paint, but anyway. And essentially we iterate through each individual tile in here, right? Look up that tile in the atlas and then copy the pixels of that tile to the pixels of the final grid. Right, that's essentially what we're doing in here, and we have to do that for each individual tile in here. For each of them, we're just looking up the corresponding tile in the atlas, and we're copying it in here. Right. So, and after that, we're just displaying the grid. Right. So just display grid, basically taking the pixels that we generated in here, right? Taking all of these pixels and putting them on screen with whatever means we have. It could be X11, it could be like Windows, whatever. We're not supporting Windows, but I mean, yeah, you can do whatever. It's just like an array of pixels. And this is where we end the frame, right? This is where we end the frame. So this is how the rendering looks like right now. And yeah, so this step is trying to be fast and optimal, but in reality it's really not, because we're constantly recreating and waiting for threads in here. And what we'd like to do is to actually sort of spawn these threads and being able to tell them, okay, the time has come to regenerate the atlas, go. Right, and then we need to be able to wait until all of the threads finished generating the atlas, and then tell them, now suspend until the next time I tell you to regenerate it again. Right, but that should not involve, recreating the threads. The threads basically have to perform the task, and they have to suspend and sleep until we tell them the time has come to do that again. Right, so we can synchronize everything to the FPS, and we won't have to recreate the threads over and over again. So that's what we're trying to do in here. And maybe in the future, we're going to extend that idea and parallelize grid generation and grid rendering as well, and maybe we'll be able to do that with the same thread pool that we're using right now for the atlas. So maybe the entire sort of like generation over this single thread is going to be parallel, right? And it's going to be in several phases or something like that. At least that's the plan. Sounds good, sounds Gucci, sounds Tamaguchi. So let's go and discover Pthread barriers, right? Because I think Pthread barriers are the thing that we'll need in here. So let me see. Pthread barrier, and I don't even have a man page for that. Okay, so let's actually take a look at some of the things in here. What are the functions that we'll need? So there's a barrier init, but I'm not sure if that's the function, because I cannot find the man page for barrier. So Barrier init. So the idea of the barrier, right, is that, how to explain that? Like, I don't want to go into the explanation because it's really sus that I don't have a man page for this function, right? I have a man page for pthread create, right? But not for the barriers. So do I even have the barriers or something like that? Let's actually confirm that I do have them. I'm gonna try to put them into my source code, right? Like this. I'm gonna just try to call this function, and let's see if it's gonna compile. So implicit declaration of the function Pthread Barrier init, which is kind of sus, not gonna lie. So maybe you have to include something else. Well, I do include pthread.h, but I don't see anything in there. Do I even have anything related to barriers in here? So here's pthread create. Do I have create? It's not even here because there's shit ton of different headers and stuff like that, and it's just like, yeah, thank you so much. Do I have to include some sort of a macro for them to appear, or I don't even know why can't I just use the thing I want to use? Why does it always have to be some sort of a bullshit that prevents you from just using the thing you want to use? It's always like that. It's just like people normalize this kind of shit. Okay, so here it is, and I see. So this is because of the C. All right. So I was expecting that C would tell me, bruh, you call it with not enough arguments, but instead it thought that I'm trying to call a different function. Is that what it thought? Oh my god. Okay. So come on, just run implicit declaration of the function. Okay, so but that's very strange. Like just tell me that I'm using the function incorrectly, right? Just tell me that I'm using function incorrectly, and I would be happy. Let's put null in here. Let's put null in here, and let's put 0 in here. There we go. So can I run it now? It's still implicit declaration. Would you look at that? That's really sus. Okay, so let's go back to user include. All right, so grep rn pthread barrier init, right? So where is it? It's in here. Initialize barrier with the attribute, and for some reason, even though oh, it's behind a macro, of course. All right, it's behind a macro. It's behind a use x open to k. So does it even say anywhere in the documentation about all of that? It says something about POSIX something, but it doesn't tell what you have to include. What is this macro? So why is struct defined only if use x open? Yeah, people are talking about that. So yeah. Short answer, if you're using glibc with APIs that are not part of the standard libc or anything instead, will enable a couple of, okay, long answer, blah, blah, blah. So, okay, this is very interesting. So it's one of those cases where I have to include some stupid macro, but do I really need to do GNU? Maybe I can just do something like, you know, yeah. Define GNU source or something. Is that what you want from me? I think that's what it wants from me. This is not what I wanted. So is it gonna compile? Okay, finally. Okay, that's actually pretty cool. Null argument where non-null required. Oh shit, that's cool. Wait a second. How do you say that? How do you indicate barrier init restrict? Huh. So it's some sort of a GNU extension that lets the compiler know that the value is not nullable. That's actually pretty cool. I didn't know that GNU had something like that. Okay, no argument, null required. So I want to just see. I'm pretty sure it's a GNU extension. GNU. GNU. Restrict pointer aliasing. It's probably basically restrict. Specify restrict because you cannot compile C++ by specifying. Okay, so it's just a backward. Okay, sure. All right, that's pretty interesting. So basically, we had to indicate that our source code is GNU source, whatever that's supposed to fucking mean, and now we'll be able to even like call barriers. So the idea of the barriers is that you provide the count. So that's the most important thing. You provide the count, and the count is the amount of threads. It's the amount of threads. Look, in a thread, once you finish your job, right? So you did some stuff, right? So you did some stuff, and then you can say something like barrier, Pthread barrier, wait, and is that how? What's the amount of arguments for this function? I don't know. Where is the function? Yeah, and it accepts some sort of a barrier, right? So we're gonna have some sort of a global barrier in here, right? Like this, and then I can say wait barrier. And you kind of want to do that also inside of the loop, right? Inside of the infinite loop, right? You did your job once, and you just wait. Right, and since you may have several threads that wait, right, so all of them will start waiting on a single barrier, right? Every time somebody waits on that barrier, the internal counter of that barrier increments. And as soon as it reaches the count that you provided while initializing the barrier, all of the threads simultaneously unlock, right? So essentially, you have several threads, they're doing their job, and they're doing that up until they hit the barrier. And as soon as everyone hit that barrier, it's lifted and they continue running again and doing something. So basically, it allows the threads to synchronize at some particular point, which sounds roughly as what we want, believe it or not. It's roughly what we want, because we want to have a bunch of threads that re-render the atlas, each of them re-rendering their individual sequence of tiles, and then we want them to stop and wait until we finish generating the grid, rendering the grid, displaying the grid, and go again to regenerate the atlas, right? But here's an interesting thing. So if they all hit the Gen Atlas, right? If they all hit Gen the Atlas, they will unlock. We have to tell them to stop, and then we need to wait until all of the steps are done and run it again. So how can we even do that? How can we even do that? That's a very interesting question. So, yeah, I think I need to make another break because I've been again talking too much. I just need to make a very quick small break. And after the break, we'll see how we can use barriers to actually implement this entire thing. All right, so let's just try to go ahead and implement that, right? So because I'm trying to think about the problems that we may encounter while using the barriers, I don't think it's the right thing to do because we don't know yet. We need to start implementing the thing, and that will reveal what kind of problems we may have. So let's just go ahead and do all of that. So let's first create the barrier. Right, so if I understand correctly, I just need to create a barrier object, right? So, and I'm not sure if I need to care about the attributes. I think I should not. So barrier object, I wonder what is the barrier object? Okay, so is it defined somewhere here? It doesn't look like it's defined anywhere here, but we might as well just grep for this entire thing in here and see where it is defined. So it's just a basically type def for UV barrier, whatever that's supposed to mean, and some sort of like a structure and whatnot. Yeah, it seems to be like a structure and whatever, right? And I suppose, I wonder if it has a big size, right? I wonder if it has too big of a size. Right, can I just put it into my renderer? So, yeah. size of this entire thing, printf, let's actually put it like this, zu, and boom, size of this entire stuff, and of course exit with 0. No build run. What do we have? 32. It's not that big of a size, to be fair. And we are going to be actually creating it only like once, right? So we don't have to worry about that too much. Okay, so where's the renderer? Here's the renderer, and we need to create a barrier somewhere here. So pthread barrier T. How are we gonna call it? Atlas render barrier. So that's what we're gonna call in here, right? Atlas render barrier. So renderer realloc. We're reallocating some stuff in here, and I'm not sure how we're gonna be dealing with all of that. I need to, so I use this function as a way of initializing the renderer, and I'm not even sure if I can just initialize the barrier in there. Can I call this thing several times? So function creates a new barrier object with the attribute specified with attr and with the threshold specified count. If attribute is not the default, I use the count argument, blah, blah, blah. Destroy, freeze everything. The value specified is invalid. The process cannot allocate enough memory. So I don't think you can easily call this thing twice. At least I don't think so. At least I don't think so. Maybe this is something that you shouldn't even try to do. But I mean, we always call a renderer free before doing anything else in here. So we might as well, in a renderer free, try to destroy this thing, right? So call the destroy, and I don't know why I created, and I think I can just destroy it like this, right? So, and in here is going to be R atlas render barrier. So we're destroying it in here. And I have to provide the pointer, by the way. I have to provide the pointer to this entire thing. So, and apparently it may fail, I suppose, if it's invalid or there's still threads waiting on the barrier, which is rather interesting. So we'll have to also keep track of the threads somewhere here, right? So we're going to have something like pthread t threads, and the amount of threads is going to be equal to the amount of threads we have in here. So we're starting to move this thing in here. So, and it's rather interesting because it looks like we have two different entities in here. One that is responsible for you know, storing the memory, and one that is responsible for managing the threads, and it kind of looks weird, but let's just continue implementing and maybe it will become more clear what the hell is going on, right? Maybe it will become more clear what the hell is going on. So, and at the beginning, we have no threads created, right? So maybe we need some sort of a flag that indicates that no thread were created, or something like that. So it's kind of sus, not gonna lie. Anyway, so let's just not think about it too much. Let's just like implement things, right? So the more we think about this kind of stuff, the less we actually implement, right? So what is it called? Atlas render barrier, right? So, and then I'm gonna use the default parameters. And here I would think that I need to provide the amount of threads, right? So for this specific barrier, I need to provide the amount of threads. But here is the interesting thing. As soon as all of the threads hit that barrier, they're gonna restart. But I don't want that to be the case, right? As soon as all of the threads of the Atlas rendering hit the barrier, I want the, you know, the main thread to resume and finish the rest of the work before telling the threads yet again to repeat their stuff. So that means I think I'm gonna do +1 to include the main threads, right? So the main thread. So we're gonna have all of the like child thread and the main thread, because the main thread also gonna wait on that barrier for the child thread. And so after the main thread resumes, I suppose, yeah, they need to continue waiting, right? Even though everything resumes, they need to continue waiting. I suppose we'll need to have another barrier, right? So the first barrier just synchronizes all of the threads and the main threads, and the second barrier makes the child threads wait until the next round. I think that makes sense. Yeah, let's actually do that. So this is the Atlas render barrier. And so what's going to be the second barrier? I don't know. Restart barrier. Let's call it restart barrier. Right. Restart barrier. I wonder if I can actually visualize the thing that I'm talking about. So this is the Atlas render barrier. So, and here are all of the child threads that are going towards that barrier, right? They're going towards that barrier, including the main thread, right? Including the main thread, right? And then as soon as they all hit this thing, there is essentially a restart frame. Did I call it restart frame? Yeah, restart. So the restart barrier, restart. So all of the children hit that barrier yet again, right? Like so. And then the main thread, this one is the main thread, doing the rest of the work, rest of work, and then hits that barrier again. And since the threads are in the loop, right, all of them are gonna just basically go again, right? So all of them are gonna go again, and the same is gonna be probably true for the main thread, right? So I think that's how we can organize all of that. So with two barriers, right? So the first barrier basically synchronizes the process of rendering the atlas, and then the second one waits for the main thread to finish the rest of the work, right? Of course, this is not how it's going to work at the end, because we're going to put more and more work into the thread pool, right? And it feels like we're going to have more and more barriers in the future to actually synchronize different phases of work. I'm not sure if this is how we're supposed to use barriers, but it feels like a very good, you know, job for them. If I'm wrong, maybe we're gonna learn something about that. We'll see. So okay, so we're gonna have two barriers for now, and I need to initialize both of them. So this is gonna be init restart barrier, and both of them are going to be threads +1 to include the main thread. Okay, so, and these things, as far as I can understand, they can fail, right? So return values return 0, otherwise error number is returned to indicate the error. If successful, return 0. Okay, so maybe if not equal. Oh, and they're not returning the stuff via the error no, they're actually returning via the return code, which makes sense because it's a multi-threading stuff, so they don't want to depend on a global, you know, state or something like that. Okay, so maybe we can do something like int error, right? Int error, and if error not equal 0, we'll have to, you know, fail. Printf std error could not create Atlas render barrier because of some bullshit in here. And I wonder if I can stick this thing into str error, right? So I think I should be able to. Because it accepts, you know, error number and stuff like that. I think it's fine. All right. So let's put it like this. And the second one is going to be error yet again. Feels Golang man. Why did you say that? Sorry. Could not create restart barrier as str error. Error, something like that. So it's going to be exit 1. There we go. Cool. So we managed to create some of these things. So if I try to rerun this entire thing, command process was terminated by floating point exception. I didn't expect that to happen, but okay. So let's actually try to see where exactly that happened. Right, so I can always just run with GDB and barrier destroy. Okay, so it couldn't destroy. All right, that's very interesting. That is in fact very, very interesting. So it wasn't destroyed properly. And to be fair, oh boy, I'm not really sure how to do that. So I'm not going to try to assume how to manage this entire thing because it's probably going to be wrong. And it feels like that we'll have to separate the notion of the memory of the renderer and the thread pool of the renderer into two different things because it feels like they want to be managed slightly differently. But for now, I'm going to just keep them in the same structure because it will make it a little bit easier. So far we successfully created everything, which is nice. Yep. I wonder if we can cause this entire thing to fail because I want to see this error message in here. Alright, so let's put it like this. I just want to see if it works correctly in here. It's just straight up faulted. Okay. This is so funny. So since this thing is non-nullable, the authors of this function didn't even bother to check for null. But I mean, the null check is easily disableable, so at runtime you still don't have any null check. But maybe it's needed for performance reasons, right? So to not perform too many null checks or something. I don't know. I know nothing about this kind of stuff, so I'm not gonna even pretend that I know why you would want to do that. Okay, Atlas render barrier. Okay, so we'll just create that anyway. Cool. So we created a bunch of barriers, and when I do the render, okay, so render Atlas. What we want to do in here, we want to create threads only once, right? And we don't want to create them all the time, right? We don't want to create them all the time. So maybe we're gonna have some sort of the Boolean flag, right? Some sort of a Boolean flag that indicates that the threads are created. Threads created. It's not a perfect solution, but I don't know how to implement that better yet because I don't have enough information, right? I simply don't have enough information to do anything about that. So let me see. It's gonna be R. How is it called? Threads created? False. They are not created yet. Right, they're not created yet. So we do a render Atlas, and as we create those things, so we also need to pass them some sort of parameters, right? So we need to pass them some sort of parameters, which is also an interesting thing, right? Which is also an interesting thing because they need to live for a while. These parameters need to live for a while, and I don't really know where to put them. I don't really know where to put them. My neighbors are doing something weird. I'm not sure if you can hear them. Yeah, as I already said, it really does want to be separated into two separate things, but I'm not sure if it needs to be. Maybe we're going to have two functions for the for initialization. So we're going to have a render realloc, right, which allocates the memory and stuff like that, and it can be reallocated at any point. And we need some sort of a function called renderer start threads, right? So renderer start threads, which accepts the pointer to the renderer, right? Which accepts the pointer to the renderer and creates everything related to threads. So that way we don't really need threads created, but maybe we do need threads created or something like that, just to assert whether this kind of thing was initialized or not. I think it does make sense. Right, so by default it's going to be null. We're going to move everything in here. Right. Okay. So create thread pthread create. Okay, so we have something like this in here, and let me just take this entire piece of code and see how we can adapt it. It's not really wise to start the threads before we initialized all of the barriers, right? I think it's important to initialize all of the barriers first. So we don't have any threads in here. The threads are stored now within the render itself, so we can remove this thing. We're iterating through all of the parameters. We fill up all of the parameters, so this is the stuff. So yeah, it feels like we used to actually put a lot of information in here for the renders and stuff like that. But this information can change in the future if the renderer was reallocated. And if it was reallocated, all of that stuff is going to be invalidated. Okay, so there's a lot of stuff that probably requires to have an access to the whole renderer, right? So you probably require an access to the whole renderer, unfortunately. Which is fine, we can make it global. It's not that big of a deal, but it's not ideal, I think. I don't think it's an ideal thing. Okay. So, render atlas thread. Render atlas thread. So we also need this thing in here, right? Let's go back. I'm gonna just put this stuff here. Render atlas thread. Where is the render atlas thread? And I'm gonna just move this stuff in here as well. So we have these things in here. So, and all of that, a lot of this information can be taken from the renderer itself, right? So if you have a pointer to the renderer, that's totally fine. So we also pass BLTR step. It's basically the amount of tiles that you have to step to do all of that. To be fair, this information can be taken implicitly from the amount of threads. So I think we don't really care. Right, we really don't care. And BLTR start is basically the index of the thread. So these are only two pieces of information that needs to be passed into the into the thread. This is only two pieces of information. So in here we are extracting the parameters, right? And I suppose the next thing we need to do, we need to extract the renderer itself from the parameters, right? So this is going to be that. And we also need to extract the starting position from here. So it's going to be something like params BLTR start. And I suppose after that we can forget about these parameters, because we really want to forget about them because they are allocated somewhere on the stack in the main thread. So it's better just extract all that and forget instantly. So I'm thinking that I'm gonna even do some sort of like a trick in here that will trigger the compilation errors in this code, because the params is not visible anymore, if you know what I'm talking about. Right, so this one is going to be null, this one is going to be 0, right? And then we're initializing this entire thing, and then we are setting this stuff in here. So that will cause compilation errors in this piece of code later, and I'll go and just fix them appropriately. Okay, so, but here is an interesting thing. So we extracted all of that stuff, and as we start this thing, we want to essentially wait for the restart. Yes, that's what we want to do actually. We want to wait for the restart. So we're going to have an infinite loop in here, right? Some sort of an infinite loop. Right, and we're going to start waiting for the barrier, for the restart barrier. Barrier wait. So let me see. So this is going to be R restart barrier. Okay, cool. So as soon as this thread starts, we're starting to wait for the restart barrier. Right, we're starting to wait for the restart barrier. So we're extracting all of the necessary information, right? So that's fine, and we just do that. So I wonder if we have enough time to do that. So it's kind of a dangerous thing. It's very, very dangerous. Man, I really want to be able to like only pass a pointer to the renderer. Is it possible to... I think it is possible. I think you can infer BLTR start from the ID of the thread, completely eliminating render atlas thread params. This is genius. Okay, so you can create the thread, right? You can create the thread, and we'll put the threads into the renderer themselves. Is there any way in pthreads get the current ID of the thread, if you know what I'm talking about? Is that a thing you can do? I think it should be the thing that you can do, but maybe not. It's kind of hard to tell. All right, so let's actually not think about it too much because we're never going to finish. All right, so here we're going to wait, but it actually makes me a little bit paranoid. So to do, make sure the params live long enough that we can extract info from them, right? So that's very, very important. If we get it wrong, something bad may happen. All right, so after we finish doing the work, we can wait Pthread Barrier on the Atlas render barrier. Okay, so we're essentially waiting for the rest of the threads. And then as soon as all of the threads hit this barrier, including the main thread, they're going to repeat this loop and hit this barrier again and wait for the main thread to restart them, right? Wait for the main thread to restart them. That's what they're waiting for. That's what they're waiting for. Yep, that's the idea. So the most important thing here is that as soon as you start them, they're not gonna do anything special. So here we don't really have the step doesn't matter. All of that doesn't matter. The parameters now only have the renderer, right? So here's the renderer. Do we have an access to the... Yeah, we literally do have an access to the renderer, and we just start this thing, and we started for the threads inside of the renderer. Right, so, and now it would be nice to make sure, that everyone got the information about themselves appropriately. So maybe we could have some sort of another barrier in here. I don't know, like you know, the actual start barrier. So we do have restart barrier, right? We do have restart barrier, but do we have a start barrier? So that sounds like a very interesting idea, to have a restart barrier. Because we don't really want to start this shit right away, if you know what I'm talking about. So do I want to create such barrier? Do I really want to do that? Is that a good idea? And will I be able to actually get rid of it later? Will I be able to get rid of it later? So yeah, let's actually create that barrier, because I don't know what's going to be the best way to do that, so it's better not to assume, right? So we're going to have like barriers for different phases, right? So we're going to have a Pthread barrier, start barrier, right? Start barrier, restart barrier, right? And then you know, stuff like that. Maybe it could be something like init. This could be init, right? Because we're waiting for the initialization of all of the threads, right? And then this one could be start barrier. Yeah, so something like that. Render start threads. So here we have the init barrier. So I'm gonna do it like this, so I can move the code around as much as I want. So init barrier, could not create init barrier, right? Then the second one is going to be start barrier. This is where we start the frame. And then we're going to have Atlas render barrier. There we go. So these are the phases of these things that we have. So then we are initializing everything. We're creating all of the threads. And after that, I'm going to be doing Pthread Barrier wait, right? I'm waiting as the main thread on until all of the threads are finished their initialization, and I'm waiting specifically on init barrier, right? I'm waiting for on the init barrier, and after that, as soon as we we need to do something like this. This is going to be init barrier. This is going to be the start barrier, right? There we go. So these are different phases of the thread. Here we are extracting all of the information and then waiting on this thing until everything is initialized, and then the main thread will signal to start rendering, and then it will signal to wait and stuff like that. Okay, so these are basically different phases of this thing. Cool. And after that, I suppose I can do something like threads started, right? Threads created, and we can make it true, right? And render atlas. Where is the render atlas function? So it accepts that. It doesn't really need to do any of these shenanigans anymore. So I'm going to remove that. It would be nice to figure out how to not recreate the threads on each render. This is exactly what we're working on right now. So I was thinking about that while writing this code, you see? Yeah, that's pretty cool. So let's actually remove that, including that to do, because that's precisely what we're working on right now. We're working on that to do. So can we get rid of the Pthread dependency on Linux completely and just use the clone directly? That sounds like an interesting educational idea, but that will require implementing our own barriers. I wrote this thing at the time when I didn't really want to use any synchronization primitives from Pthreads, so I'm not sure if this thing is still relevant, but it would be nice to actually, you know, explore how you can do multi-threading in Linux, without Pthreads. But since we're already using barriers, I think this educational thing could be outside of the scope of this specific project. I'm gonna actually put a note for myself. So multi-threading with clone, and I'm gonna add that to my to-do list on things to stream about, right? So there we go. So, and it's outside of the scope of this project, so we don't need to do that anymore, right? And we don't need to do that anymore. And essentially render atlas, right? So I want to do render atlas. At the time when I'm doing the render atlas, right? Render atlas thread. There we go. Everyone must be waiting. Everyone must be waiting on the start barrier, right? And another thing I would like to do, I would like to assert threads created, right? So it's very important. Then we're gonna do Pthread barrier wait on start barrier. There we go. We're waiting on the start barrier. And as soon as everyone hit that barrier, the threads start rendering its thing. They start rendering its thing. Then the main threads waits on the Atlas render barrier. Atlas render barrier, right? So indicating that the rendering has finished, right? And after that, everyone is going to be waiting on this barrier yet again. Hopefully, that's how barriers work. I'm just realizing, is that how barriers work? So they reset their counter to 0, right? So am I using them correctly? Check if the required number of threads reach the barrier, right? So I think that's how they work. That does make sense. Okay, so rendering the atlas is essentially just waiting on 2 barriers, right? So through that, we're signaling to the thread pool that we want to start the rendering, and through that, we're basically letting the thread pool to let us know that it's finished its job, right? Okay, so I think I've done the whole refactoring and restructuring that I wanted to do, and I think the time has come for compiler assisted refactoring. So there's a lot of compilation errors in here. I just shaped the code to the way I want it to work, and let's just see what kind of problems it creates. So let's try to recompile the entire thing. I'm not going to try to run it. Okay. What do we have in here? Atlas thread. Okay, so this thing does not have invalid argument, which is... Oh, okay. Oh, we already actually destructurized it. Okay, so that makes sense. Init barrier, so incompatible type. Really? Do I have to... I have to take a pointer. Okay. So that means I have to take a pointer in here. All right. So it's probably have to be pointer in all of these things. All right. So BLTR start does not require the parameter in here. And the step, let's actually put it like this. Might as well call it BLTR step. Right. Is going to be equal to the amount of threads. So that's kind of the point in here. So this is the only step that we have in here. And do we have anything else? Params. Okay, so all of this stuff can be probably taken from the renderer itself. Right, so it is taken from the renderer itself. Another one, generate tile32. Okay, so this function, generate tile32. So let's actually hoist it up a little bit. Generate and put it above that thing so it can be used properly. So params, so this is the Atlas, and yet again I suppose it can be taken from the renderer. All of that stuff is basically part of the renderer. So what about params in here? Let's actually do R. There we go. And what else do we have? Params are okay. Oh yeah, so this has to be a dot. Init barrier, incompatible stuff. Okay. So what do we have? Pointers yet again. Okay, it compiles. So that should be it, I suppose. We don't really actually call start threads yet anywhere. But for that, I have a preemptive measure. So essentially, if you try to render Atlas while none of the threads were initialized, it's going to cause a runtime error. Right, so let's actually see if it's going to do anything. So it's going to be no build run, and it should cause a runtime error. There we go. So no threads are created. So it was trying to run the entire thing, but it didn't work. It didn't really work. So realloc threads, render realloc. So we do that at the beginning of the program, right? So a renderer start threads, and we can just provide a pointer to the renderer, and that should be it. If I recompile the entire thing, it should be fine. Let's try to run it and see if it's gonna crash our entire system. Well, it didn't crash the entire system, which is rather interesting. So, and we also don't really clean the threads at all. So looks like a right thing to do. I mean, let's actually put the background in here. So black. Don't see any problems in here so far. This is kind of sus. The fuck? Okay, and then let's take a look at the grid. Right, at the grid. PNG grid looks fine. Just like, yeah. All right, so let's try to do that live. Okay, live works. But can we somehow confirm that it became faster? It's kind of difficult to confirm that it became faster. It probably didn't become faster, but at least we're not constantly recreating the threads, which is kind of cool, right? So we're not constantly recreating the threads. It seems to be working. It seems to be working. So let's actually do a couple of measures. So we have all of the changes in here. So let's create a separate branch called thread pool, right? So this is going to be thread pool, and try to not recreate the threads on each frame, right? So, and I'm going to push that right into the repo. Right, we're gonna push that right into the repo, mate. Right into the repo. And so let's first compare the performance, right? So in the main, if I understand correctly, we're rendering a slightly different shader, right? We're rendering the digit frame shader. So to be fair, let's actually go back to Pthread spool and change the shader back to its original one, right? And also you may notice that maybe there are some discrepancies between how the tiles are displayed in offline mode and live mode, and this is because the X11 just treats the pixels differently, so it's a whole different story. So I'll fix that at some point, but it doesn't really matter. So yeah, digits, blobs, digits, and where's the colors? Here are the colors. So when I suppose we wanna have the colors that are black and white. Okay, so let's recompile the entire thing, and if I try to run it, okay, so it seems to be working. What about the live? Whether it's faster or not faster, it's kind of hard to assess, to be fair, and we're also streaming, and it's a little bit laggy as well. So, okay, so switch shader back to digits, right? Let's push that right into the repo. Okay, so let's go back to the master and let's run the rendering a couple of times. So yeah, right now the rendering takes 3 milliseconds, around 3 milliseconds, right? Sometimes it's 8, sometimes it's that. We might as well also disable the output of PNG, right? So, and then you can just take a look at the total, and it's around 3. So there's no much benefit of not recreating the threads here, because we're rendering literally a single frame. So it all makes sense if you have several of them. But I mean, yeah. So I'm pretty sure there will be not that much benefit in here. Okay, so let's actually go to the thread pool and let's do that thing. And yeah, it's pretty much the same thing, right? It's pretty much the same thing, but what I want you to see is that it doesn't really crash anything. So yeah, it works identical to how it worked before, which is nice, which is cool. So that's fine. So and now, since we're not recreating the thread, we can even also confirm that it's constantly recreating the threads. I remember seeing a pretty funny picture in the htop. Right, so if I run this thing, right, so let's actually put it into a separate thing, and htop, and let's just search for Wang tiles, right? So, yeah, it's constantly recreating the threads. You can kind of see that it's constantly doing that. So here's the threads, and they at some point will die, right? So they constantly appear and disappear and stuff like that. So it's kind of lame, right? Wang. So let's actually keep this in here. And now, if we switch to the thread pool, let's see how now it is going to look like, right? So is it recreating the threads? Doesn't look like it. So it's just created 5 threads, and it's just using 5 threads. That's it. And it works exactly as it worked before, right? So yeah, it doesn't recreate the threads. We also don't really kill the threads appropriately, right? We just exit the application, and I suppose that kills all of the threads, right, for us. So yeah, maybe we'll have to put it to do there about that. Render atlas threads Threads are not finalized properly. At the end of the application. Okay, so I have the next idea, actually. I have the next idea. Can we... Can we now parallelize the render grid? What's funny is that we generate the grid on each frame, because we don't really change the grid at all. Right, so live rendering with xlip, So yeah, we generate the grid once, and on each individual frame, we're simply render the atlas, and then we render the grid. So what if render atlas thread? In a render atlas thread, we would have another loop in here, right? Another loop that basically does the same thing, but for the grid. And then we're gonna have another barrier in here to wait for, right? So you can have like several phases and whatnot. Yeah, that's pretty cool. Yeah, so you can use the same thread pool to render both the atlas and the grid. How cool is that? I think that's pretty cool, right? So you can, yeah, you can literally use the same thing. I wonder how difficult it is to implement. So, all right, so let me actually remove that, and let me find the render grid thingy. And essentially, it's the same thing, except in rendering, you're copying from the atlas, right? You're just copying it there. And I even have a to-do for that, like parallelized grid rendering. So, yeah, okay. It's kind of cool while implementing something, you actually encounter these to-dos and realize, okay, I was thinking about that in the past as well, right? So I sort of like envisioned that it's going to happen. Anyway, so I think before we try to parallelize the grid, and maybe as soon as we parallelize the grid, maybe then we can actually see the benefits of doing this entire parallelization, right? Because right now grid is like straight up sequential, so there's nothing special in there. But as soon as we parallelize it, that could be useful. So let's actually create a to-do, and I think I want to make a small break. I'm going to refill my cup of tea, and after I refill my cup of tea, we're going to try to parallelize the grid rendering, and maybe then we'll see something useful in there. All right, let's finish this off. So it's already dark in here. We need to parallelize the rendering of the grid. We're not going to parallelize the rendering of the generation of the grid, because it's actually really fast. If you take a look at the stats, right? If you take a look at the stats, the grid generation is 13 microseconds, not even milliseconds, 13 microseconds, and we're not doing that on each frame. So that's kind of the thing. We're animating the grid, but the actual specific tiles of the grid stay the same. We don't call this thing on each individual frame. So this kind of stuff, it doesn't really matter, right? So yeah. Live, yeah. As you can see, we just generate the grid at the beginning of the entire thing, right? And then inside of the event loop, we're only calling to render atlas and render grid, and this is the only operations that are important for us to be fast, right? And that's why we are parallelizing them. Okay, so let's introduce yet another barrier, right, to the party. So here we have an atlas renderer barrier, and I suppose we'll need to introduce another one, grid render barrier, right? Grid render barrier. So at the beginning we render atlas, and then we're gonna call this thing yet again, and it will generate the grid. So, and I suppose this thing should happen like simultaneously. Yeah, they should happen simultaneously. Okay, we'll see how we're gonna approach this entire thing. So let's just go ahead and just initialize everything that is needed to be initialized. Start threads. So here we're creating all of the barriers. Maybe it would make sense to actually compose all of the barriers into an array and have some sort of an enumeration, because yeah, that's actually sounds like a very interesting idea. Anyway, so but we're gonna do that a little bit later. So grid render barrier could not create grid render barrier. Atlas render start init. Everything seems to be okay. Right, and we're waiting for initialization of those things. So because of that, render atlas thread probably should be renamed to something. Let's just call it render thread, and the parameters are going to be render thread parameters, right? So, and I'm not going to fix the rest of the naming because it will be caught by the compilers, so it doesn't really matter. So here we have atlas render barrier, and then we're going to be waiting for the grid render barrier, and in here we're going to be doing like a very similar thing as well. Okay. So let me just quickly sip and then we'll think. Render grid. So, and this is what we're trying to parallelize in here. Right, I even created a to-do. That's precisely what we're doing. That is in fact precisely what we're doing. So we're just iterating through this entire stuff, and we're going to be doing that in a very similar fashion, right? In a very similar fashion. So let me compute the whole amount of cells that we have, amount of tiles. So grid TL size, right? Grid TL size, and in reality it's just basically a product of width and height, right? Product of width and height. So that's the entire thing. And what effectively we're doing is computing the tile. So it's the tile starts from, this one is rather interesting. So the tile that we have to start with is kind of implicitly equal to BLTR start, which is rather freaking interesting. So BLTR start indicates not only where to start for the atlas, but also where to start in the grid, because it's pretty much the same thing, right? If you are starting rendering from this one in atlas, you're starting rendering from this one in the grid. If you're starting from here, you're also starting from here, and so on and so forth. So it indicates the start point for any sort of grid. So I don't think it should be called BLTR start. I think it should be just called the start, but it also can be interpreted as BLTR as well. So it's kind of a, we were making too many assumptions in here, but that's fine. That actually allows us not to pass too much stuff between the threads, right? It's kind of interesting. What I learned while doing multi-threading, right, is that you can either choose to pass information between the threads, or you can infer information implicitly, and in that case you don't have to pass anything and you don't have to think about synchronization and stuff like that. It feels like in multi-threading it is preferred to implicitly infer a lot of information so you don't have to deal with synchronization and stuff like that. At least that's what I feel like. I'm not a professional in multi-threading or concurrency or any kind of stuff, but while doing that, it feels like, yeah, that's what you want to do. You want to infer a lot of information as much as possible, so that way you can avoid the problems. But you can kind of create other problems, because some of the information that is based on assumptions, right, it's kind of dangerous, because what if the assumptions have changed, right? So it would be kind of cool to have a language that would allow you to encapsulate these kind of assumptions in a type system, right? And check that, maybe not even a type system, but maybe in some sort of a meta program, right? That would execute, and in all of the necessary places will just check if the invariants haven't changed or something. That would be kind of cool. But I don't know, we'll see. And at the same time without being an annoying piece of shit, of course. So let's continue. So tile less than the grid tile size, right? It's kind of difficult, like for the languages, it's kind of difficult to like not to cross the line between being actually useful and actually annoying. So and that line is really, really blurry. So if you push it too much on amount of checks, you go into being annoying territory without being helpful, right? So yeah, it's kind of difficult. The development languages is actually kind of difficult. Anyway. So what do we have here? So here's the tile. So then I need to infer GWTL and GXTL from the tile itself, right? So let's actually do something like GWTL, and that is effectively tile divided by the grid width, right? So if the row size is the grid width, right, you take the number of the tile and divide it by the size of this thing, you get the y, right? And the x correspondingly is going to be mod of this entire thing, and there you go, you've got yourself an x. And by the way, plus plus, it has to be plus BLTR step, right? So that's what we're doing here. That's a BLTR step. Maybe we could do BLTR step actually somewhere here, because apparently it's this, it wants to be reduced like this. All right, so here's BLTR step, and in here, I guess what we're effectively doing in here, we are just repeating this piece of code, I think. Yeah, so it's just like a matter of changing how you iterating stuff, right? So, and here we're just repeating all that. There we go. And we can remove this stuff. So instead of iterating like row-wise, column-wise, we're just iterating one by one and with a step, with the step equal to the amount of threads. And yep. I'm not sure if that's a good idea, because it feels like if the amount of threads is too big, you can have a lot of cache misses. So maybe you actually want, well, here's an interesting thing. The tiles themselves are not really located sequentially in the memory anyway, so you're gonna have cache misses no matter what, right? So it's not particularly helpful. So maybe there should be like some sort of a strategy that, you know, well, it's not really about being continuous memory, right? Because also CPUs look not only on how sequentially you access the memory, but also trying to see any predictable patterns, right? So if you're jumping with a regular step, the CPU may actually notice that and may start, like, you know, prefetching some stuff into the cache in a similar pattern as you just iterate over the memory. But I know nothing about this kind of stuff, so don't listen to me. I'm just assuming shit. Right. Maybe it's not how it works. Anyway, so let me try to compile the entire thing, and what do we have in here? So render atlas, yeah, so we renamed this entire thing. Let's quickly rename you know, this stuff. Oh shit. Okay, so okay, this is the second one. Boom, I'm gonna do that through the entire code base. So this thing needs to be a little bit higher, right? Just a little bit higher. Boom, and I'm gonna put it in here. So we have two very important functions in here that generates the tile and that copies the file, the tile, right? And that's what we're trying to parallelize in here, I suppose. So these like basic operations. Render thread, not render atlas thread, but render thread. And this thing suspiciously compiles. Like, why the fuck does it compile so easily? Okay, and I hope I didn't make any stupid fucking mistakes, man. Hopefully. So yeah, as soon as you do that, as soon as you wait on this thing, it will instantly start rendering the grid, like instantly. So I suppose we want to get rid of the notion of render atlas and render grid. We really want to get rid of these two notions, right? Because these two notions turn into just waiting on the corresponding barriers. That's it. Surprisingly, actually. So we want to have like a single function. Something like void render. Render, it could be just to render the grid. We can just merge these two things together into rendering the grid. Right, so the first thing we do in here, we're just waiting on the start, indicating that the time has come to start the whole process. Then we're waiting on the atlas to synchronize all of the threads with rendering on the atlas. And then we're waiting on the grid renderer. And after that, the threads, render thread, Render thread. The threads will wait on the start barrier, right? Basically wait for the next iteration. And between this thing and this thing, the main thread will try to take the pixels that were generated by the threads and just put them out either into a PNG file or into the screen or something like that. So, yep. I guess that is it. I hope I didn't make any stupid fucking mistakes, man. Let's actually try to recompile this thing. So render atlas, we don't have a render atlas anymore. And now, what else do we have in here? Oh yeah, this one is interesting now. So since we don't have these two separate things, yeah, these two separate things, we cannot just do that. As already mentioned in here, grid generation is completely independent from atlas generation, right? Which is rather interesting. So I think now we need to change the grid generation in here. So we need to pre-generate the grid first, and then we're only going to have a grid rendering, right? So a grid rendering also includes atlas rendering. So it's kind of difficult to measure atlas rendering and grid rendering separately because they're all mushed together by the thread pool, right? So all of that happens by the thread inside of the thread pool, right? So okay, well, it is what it is, and it isn't what it isn't, I suppose. Okay, let's try to compile the entire thing, and it seems to be compiling. Let's now remove all of the PNG files, and I'm going to try to run this entire thing, and hopefully it's not going to crash or anything. And okay, so let's actually do null PNG, and yeah, it seems to be doing that relatively fast. I'm not sure if it's actually better, but in any case, let's actually take a look at the atlas, black atlas PNG. So atlas looks fine. What about the grid? Grid looks fine. So yeah, it's kind of sus, not gonna lie, but let's actually try to run it live. And it doesn't really feel any different. That's the problem. Right, it's probably parallelized, right? And Wang tile. So all of the threads are doing things, you see? Like all of them are like busy doing shit. But the entire thing is still a little bit choppy, and I think this is because of the X11. So for the X11 we need at least like, I don't know, double buffering or something. We'll see. But yeah, it's doing things. So one of the threads is actually working more than the others. But apart from that, everything seems to be working and twerking correctly. At least we didn't break shit. So maybe we can't see any benefits because we're rendering very small things. If you know what I'm talking about, right? They're very, very small. So anyway, let's actually commit whatever we have. Parallelize grid rendering, right? So there's no much difference between atlas and grid rendering anymore because it's basically happening inside of the single render thread, right? Render thread. So I suppose we want to try to actually render things on a bigger scale. We can always increase the size of the tile, right? So something like tile width is going to be 128 and tile height is going to be 128. So now it's a little bit bigger. So it's 15 milliseconds, right? And I wonder, so yeah, as you can see, grid generation is actually really nothing, right? So 14, 13. Right, and this is multi-threaded, right? All of that shit is multi-threaded. So now, if I switch back to the not multi-threaded version, is it going to be slower or faster? Is it not multi-threaded? Okay, it's the same. All right, so, well, I mean, no, not multi-threaded still have it still has the atlas multi-threaded, right? So it's not a fair comparison. What we want to increase in here, in reality, actually not the tile size, but the grid size, right? So grid width is going to be 100, and grid height is going to be also 100. So, and yeah, so it's relatively slow, and that's the actual size of the final thing in here. So if we take a look at the grid PNG, it's going to be, it doesn't really look that enormous. Oh, this is because I never saved it. Okay, so let's actually save the entire thing. So it's going to take some time to save such a huge image on the hard drive. It's going to take some time to do that. It's going to take some time. Man, that takes a lot of time. Okay, so it took 20 seconds to encode that image. But we also compiled it without any optimizations though. Okay. So, and if I take a look at the at this thing now, and what is it called? Grid PNG, right? So it's grid PNG, and here it is. That's the encoding is probably shit, but that's what we're generating. That's what we're generating so fast, by the way. If you disable no PNG, right? We're generating such a huge image in 88 milliseconds, right? So, and we're also parallelizing that, so we're doing that in 5 threads and whatnot. So if I switch to the master where the grid is not parallelized, I wonder how much time it will take. It takes a little bit more, right? It takes hundreds of milliseconds, right? It takes hundreds of milliseconds. But if you parallelize this entire thing, it takes yeah, a little bit less, I suppose. It takes a little bit less. I wonder if you keep increasing. What about 200 of these things? Right, so parallelized version is 400 of these things, and not parallelized one is it's actually fast. It doesn't even change anything. All of that shit was it's actually faster for some reason. Probably because of the cache miss as I was talking about. Yeah, probably. Huh. Interesting. Interesting. So, yeah. Okay, so, but what if we try to enable all of the optimizations? Okay, all three. So it's optimizing everything, and if I try to run this entire stuff, I wonder if it's going to be faster. No, it is not faster, surprisingly. Yeah, it is not faster. Okay, so if I do live, if I just do this original thing, oh, because it's recompiling also. Okay. Yeah. All right, that was interesting. At least we didn't break anything, right? So at least we didn't break anything. We didn't really gain any significant improvement. But at the same time, we didn't break anything, and now our thread pool does not recreate anything. So interestingly enough, this kind of stuff enables us with actually, you know, parameterizing the amount of threads at runtime, right? Because right now it's hard-coded to just 5. Maybe we'll be able to, you know, turn it into a runtime parameter. Anyway, at least I learned how to use barriers, and that was relatively useful. I hope I didn't make any mistakes while using them, but we didn't gain any performance anyway, so it's kind of strange. But maybe we're gonna explore that a little bit later. Anyway, so I hope today's session was interesting. It was definitely interesting for me, and I guess I gotta go. That was the barriers. That's how I use the barriers. Thanks everyone for watching. Yeah, thanks everyone for watching. Love you all.